From the beginning of the century, space agencies and now also private companies have started to put their efforts in sending again humans beyond low Earth orbit. This ambitious target not only implies high technology, but also the appropriate terrestrial or marine biodiversity that is essential for human survival out of Earth.
Hello, my name is Álvaro Sanz and I am the project manager and system engineer of StarWorms UC3M team. We have developed a CubeSat platform to carry the proposed biological payload that shall verify the survivability in space of roscoe worms, with the objective of assessing their potential capability of creating artificial ecosystems for future deep space exploration missions. The proposed payload consists of a 3U L-shaped structure that contains the worms, the probes, the sensor, and the cameras necessary to perform the experiments. The payload requirements impose a series of constraints in terms of orbit geometry, power, thermal control, and altitude control that drive the platform design.
The team set two main constraints to achieve the best design solution. First, follow the CubeSat philosophy, that is, find the most robust, mature, and reliable solution that complies with the requirements. Hence, only COTS equipment can be used. One sized for each component, COTS trade-offs have been performed. Second, avoid the use of propulsion system, since it's the less mature system for CubeSats, which can risk the payload. For example, risk of explosion. From this point, my colleagues will describe the mission and system design process.
Hi, my name is Miguel Renieblas. I'm an aerospace engineer by the University of Bristol, and I'm currently studying a master's in space engineering at the UC3M. My main task in this project were to perform the mesh analysis, a first design of the communications, and command and data handling subsystems.
The main goal of the mesh analysis is to define the orbit, which will impact the decisions taken for all the subsystems. Our spacecraft will be in low Earth orbit in order to avoid the Van Allen belts and to be able to deorbit solely through the atmospheric drag. Performing a re-entry simulation for the worst case scenario, this gives that the maximum altitude for re-entry in 25 years is around 520 kilometers. After this, a coverage analysis was performed to check whether the coverage time was enough to transmit the required payload data through the ESA core network with the current COTS technology. The higher the altitude, the longer the launch period, and the coverage time. Therefore, a circular dawn-dusk sun-synchronous orbit at 500 kilometers of altitude has been chosen. The communications subsystem is responsible for communicating the spacecraft with the ground stations. It will do so through two channels. One at UHF with a nominal directional antenna for telemetry and commands, so that the satellite is able to communicate and receive commands even under severe pointing misalignment of the spacecraft. And one at the S-band with a patch antenna for payload data. This will provide a higher data rate in order to satisfy the payload data downlink requirements of 550 megabytes per day. A trade-off study was performed to select the components, and these are shown here. An RF link budget was carried out for each of the links in order to determine whether the system could achieve the required data rates. The results were satisfactory. The command and data handling subsystem is responsible for receiving and distributing commands to other systems, and for collecting and processing payload and housekeeping data. A list of the main commands the system can be asked to execute are shown here, with the most important one being the preparation for decommissioning. Here, the system will have to execute a command to terminate all life inside the payload in order to meet the requirements. Our configuration will consist of two onboard computers, a main one for housekeeping, telemetry and commands, and a dedicated payload computer for image processing and storage. These have been chosen according to their compatibility with the transceivers and their compliance with the requirements.
Hi, my name is Sergio Sarasola and I'm an electronics and automatics engineer. Within my team, I was responsible for the development of the electrical power subsystem of the spacecraft. Apart from that, I was also involved in the creation of utilities like 3D models and animation. The development of the EPS is a hard process that requires significant iterations to reach the final solution. The inputs coming from the rest of the team has strongly driven the design, the sizing process, and the commercial of the cell components trade-offs. It's also important to remark that it was soon determined that the power needed to transmit the scientific data to the ground was fairly high, and also that the transmission windows were not frequent at all. with this in mind, we went for a non-conventional power strategy. We will create the EPS without the transmission power, and we will obtain the energy for that peaks from the one saved on the battery. The EPS is composed of a solar array, a battery, and a power management and distribution unit. The first step is to compute the power budget, selecting the components, its quantities, and their power requirements. With this data extracted from the different datasets, we can now compute the total power consumption of the different operational modes: save, nominal operation, and nominal plus communications. The nominal plus communication mode requires about 1/4 more power than the nominal mode. The emission analysis showed that the communication time per orbit only represents 5% of the orbit period. For this reason, an innovative solution has been taken. It is decided to size the solar array to cover the nominal mode and provide the extra power required for communications with a battery. By using this approach, the solar array size is reduced by 12 cells and power will not be wasted. After performing a carefully designed energy balance, we can obtain the number of solar cells required, 42. In addition, the battery is sized from the extra power required for communication. Here we can see a schematic diagram of the whole system that is governed by the PMAT. It is composed of one array conditioning unit that receives the power coming from the solar panels, and two power distribution units connected with all the spacecraft components, taking into account their voltage requirements.
Hello there! My name is Álvaro Arroyo. I'm an aerospace engineer from Universidad Carlos III de Madrid. I have been the responsible for the development of the attitude determination and control subsystem, and also for the mechanical design and structure of the spacecraft. The ADCS is a very important subsystem, since its performance allows to know the orientation of the spacecraft, which is the attitude determination, and in case of environment disturbances, control the spacecraft to counteract them, which is the attitude control. Our mission needs to fulfill some requirements related to the sun pointing and similarity pointing to achieve communications with Earth. This will provide information for other subsystems, like power or communications. In order to design the ADCS, several steps need to be developed. We are going to cover the steps to size our ADCS components. The first step is to look at the requirements and control modes, determined by the mission analysis and other subsystems. For instance, we have requirements of sun pointing for power of the solar panels and semi-nadir pointing for communications with Earth. This will define our attitude determination and attitude control. The second step is size the environmental disturbances for worst case possible that will affect our CubeSat during its operation, from lower to higher contribution, solar radiation pressure, gravity gradient, aerodynamic torque, and magnetic torque. To a total result, a safety margin of 20% is added to represent other small disturbances like sloshing or uncertainty in the center of gravity, getting a more conservative total torque. Then, the ADCS components will be sized to counteract the disturbances. The first components are the reaction wheels. To size them, it's necessary to consider the effects of the disturbance torque and slew torque, but also the detumbling torque after launcher release and the momentum storage. The magnetorquer will be sized according to the magnetic dipole that is able to produce. Star trackers and sun sensors will be defined by its field of view, accuracy, and update rate. And a magnetometer is integrated in the onboard computer. Finally, the components are selected from the catalog, following a trade-off analysis. For our mission, the actuators will be for reaction wheels that will be mounted as a pyramid and a magnetorquer, and as sensors, a star tracker and 3 sun sensors.
Regarding the system configuration, an extensive use of different software tools was necessary to compute important parameters, like system mass, inertia values, or COG positions. Apart from that, the IDM CIC was extremely useful to compute different system budgets, and also to obtain a preliminary 3D visualization of the different satellite components. Here we have a short animation that shows the CubeSat configuration. The antennas are placed in the bottom part. The reason for this is that it's the side of the CubeSat that will always face the Earth. Working now, the solar array deploying mechanism, and you can see 4 of the 6 solar panel columns deployed from the original positions. Now let's have a look at the back. Putting aside the main structure and some shielding panels, we can have a better look to the different components. First, the BP4 38.5 Wh battery pack. It is placed above the L-shaped payload displayed in the black color. Now the 3 main boards, containing the payload and spacecraft computer, the transceivers, and the PMAT for the electrical power subsystem. Regarding the AOCS, here there is a reaction wheel pyramidal assembly, with 4 of them attached. The magnet torquer located far away from the main boards to prevent electromagnetic compatibility issues. And the star tracker that is placed in the top side of the CubeSat to avoid blinding sources, like the air and the sand. Finally, 3 sun sensors are placed in the different panels.
My name is Miguel Muñoz, energy engineer by the University Carlos III of Madrid, studying now an industrial mathematics master's program. In this project, I've worked as thermal control engineer, since my studies match with such profile. The task that I have developed is the design of a thermal control subsystem capable of maintaining the temperature in each component inside the CubeSat inside the requirements. Basically, the units that have been selected to satisfy the needs of the mission need to operate within certain temperature range. This is not a trivial task in spacecraft development, since the thermal analysis usually involves many variables that are highly interrelated. We have developed a thermal mathematical model in order to satisfy such requirements and make complex decisions on the design of the thermal control subsystem.
Heat transfer in nanosatellites involves many different variables. Such variables can be conduction and radiation between units, external radiation received from the Sun and the Earth, radiation emitted by the satellite, or power consumption of the components. One key point of our analysis has been determining the view factors, which represent the fraction of radiation that one body emits and reaches a second body. We have made a special emphasis developing a code to compute them with an stochastic integration method, rather than classical integration, to ensure accurate results. We have developed an integration tool to obtain the temperature profiles in a non-stationary study. This has shown to be important when cyclic terms with a significant impact are considered. The results can be seen in these graphs, where it is appreciated that temperature lies within the limits at every instant of time. Finally, 2 cases have been studied. The hot case considers only expected nominal operation. However, in case that the mission wanted to be extended, a cold case including eclipses should be studied. The thermal control system design has considered all the elements of the analysis to satisfy all the requirements.
Finally, here you have the main mission budgets and the mission summary. The overall mass taking into account components and system margin is about 16 kilograms. The main contributor to the budget is the payload. This budget also includes thermal hardware, harness and shielding provisions. Besides, an estimated procurement cost budget is included in this slide. The right table summarizes the key aspects of the mission, including the orbit, launch window, system level features, and the final component selections that only relies on costs. As a conclusion, the achieved design solution complies not only with all top-level and lower-level requirements, but also is the result of an exhaustive, iterative, and optimized concurrent design. StarWorms UC3M team strongly believes that the presented CubeSat is a robust, mature, and reliable design and can serve as a starting point for future and more detailed design phases of this mission.
It has been a pleasure to participate in the second edition of the NanoStar Challenge. We have learned a lot and we have had a lot of fun.
Thanks for watching!